Energy is the essence for the sustainability of the human civilization. The anthropogenic environmental changes, however, place a premium demand for moving away from fossil fuels as a principal energy source. Among all carbon-free clean energy sources, solar by far has the incomparable potential for sustaining our current and projected energy needs. Hello, I'm Val Valev at the University of California, Riverside. Here, in my research group, we employ biomimetic and bioinspired approaches into solar energy science and engineering. Biomimetics mimic or imitate biological systems and their properties. Therefore, biomimesis provides great means for testable hypotheses and for understanding how biological systems work. In contrast, bioinspiration takes ideas from biology and uses them in an unconventional way to achieve properties that biological systems do not have. Overall, biomimetics are excellent tools for learning how biological systems work, and bioinspiration is the way to bring what we learn from biology into the applied aspects of engineering. For more than 3 billion years, solar energy has sustained life on Earth via photosynthesis. The photosynthetic organisms capture solar light and convert it into chemical energy. Therefore, photosynthesis provides the most important learning paradigms for solar energy conversion. The photosystems and the photosynthetic reaction centers are transmembrane proteins with high helical content. In addition to composing key structural protein motifs, alpha helices have amazing electronic properties. They are the best-known biomolecular electrodes. That is, they contain electric dipoles with ordered orientations. It is the orderly oriented amides and hydrogen bonds in protein helices that result in their permanent dipole moments of about 5 dBs per residue. Biomimetic approaches have demonstrated the immensely promising properties of these natural electrodes for controlling charge transfer. Polypeptides, however, cannot efficiently mediate electron transfer at distances exceeding 1 or 2 nanometers. To address such limitations, we resort to pi-conjugated polymers and oligomers. Similar to polypeptide helices, these polyaromatics contain ordered amides supported by hydrogen bonding network. Thus, they are bioinspired electrodes. Unlike protein backbone chains, the aromatic moieties of these bioinspired electrodes provide continuous pathways for long-range electron or hole transfer.
For our work on biologically inspired systems, we employ a broad range of cross-disciplinary approaches from chemistry, physics, and biomolecular engineering. We employ techniques such as rational macromolecular design, organic and solid phase synthesis, and time-resolved spectroscopy.
Hello everyone, my name is Dodo Bao, a PhD student in Professor Willoff's group. In order to study photo-induced charge transfer through bio-inspired electrodes, we need light absorbers with a range of redox properties. So my project involves the synthesis and the characterization of those electron donor and acceptor light absorbers. To examine how local electric field moderate the properties of these chromophores, I couple them with anthranil amides. For charge transfer studies, we mainly use time-resolved emission and transient absorption spectroscopy.
Hi, my name is Gokul Upadhyayala. I am a PhD candidate in Professor Volov's group. In order to study these bio-inspired conjugates, which are also anthranilomide derivatives, we need to make them. Multi-step solution phase synthesis has been the only way to prepare these oligoanthranilomides. By employing non-traditional solid phase synthetic procedures, we demonstrate the facile preparation of these oligoanthranilomides. In parallel to developing efficient synthetic procedures, we're also investigating the fundamental effects of solvent media on the dipole moment of these bioinspired electrodes. We observed experimentally and confirmed theoretically that the reaction fields of the solvated cavities can even double the dipole moments of polar solutes. Our work on bioinspired electrodes has immensely benefited from collaborators with complementary expertise, such as Professor Roger Lake's group in the electrical engineering department. While we carry the experimental work in our lab, it is Professor Lake's group that theoretically examines our hypotheses.
Although JP's chem letters has been around for a little over a year, it already has made an impressive impact for fast communication to promote advances in energy science.